We've all seen Hawkeye's iconic replays, drawing a definitive line that settles a disputed call to the millimeter. But how does a system built on multiple camera feeds achieve this almost unbelievable accuracy, distinguishing between in and out with such certainty? The secret to Hawkeye's precision lies in an intricate blend of physics, advanced computer vision, and rigorous calibration. It's not just a fancy slow-motion replay, it's a real-time 3D reconstruction of the ball's journey, accurate to a fraction of the ball's width. Imagine trying to pinpoint a specific fly in a large room using only one eye. You can see it, but its exact distance and position are hard to judge. That's why Hawkeye doesn't rely on a single perspective. Instead, it uses a network of high-speed cameras, typically 6 to 10, strategically placed around the court or field. Each camera records the ball's movement from a different angle, capturing hundreds of frames per second. The system's sophisticated algorithms then spring into action. They are trained to identify the ball, and only the ball, within each camera's view. This involves analyzing differences in pixels, detecting motion, and filtering out everything else, from players to shadows. The computer effectively draws a 2D digital outline of the ball in every single frame from every camera. Here's where the real magic begins: triangulation. Think back to how your own two eyes give you depth perception. By comparing the slight differences in the angle and position of an object, as seen by each eye, your brain calculates its 3D location. Hawkeye does this on an industrial scale. For every fraction of a second, the system takes the 2D position of the ball from at least two, and often many more, synchronized camera feeds. It then uses precise geometric calculations to determine a single, unambiguous 3D coordinate for the ball in space. But how does the system know the exact relationship between the camera images and the real world? This is where rigorous calibration comes in. Before any match, engineers meticulously map the playing area and the precise location and orientation of every camera. They use special tools to measure key points on the court or field, creating a detailed 3D model. This calibration process allows the system to translate the ball's pixel position on a camera's sensor into an exact real-world coordinate, accounting for lens distortions and perspective changes. Without this, even perfect triangulation would be meaningless. This process is repeated hundreds of times per second, generating a continuous stream of 3D data points. The system then interpolates these points to reconstruct the ball's entire trajectory, a smooth, hyper-accurate path through space. Even if a camera's view is temporarily obscured, the other cameras can fill the gaps, and the system can predict the ball's path with high confidence. It also constantly recalibrates for minor shifts or environmental factors like temperature changes, ensuring consistent accuracy. When the ball makes contact with the ground or crosses a line, the system extrapolates its precise path down to the last possible moment. The algorithms can determine the exact point of contact to within millimeters, far exceeding human visual judgment, especially at high speeds. This entire complex calculation, from multiple camera inputs to a definitive 3D verdict, happens in milliseconds, ready for instant replay and unbiased officiating. This blend of precise physics and powerful computation leaves no room for doubt. It fundamentally changed how we watch and officiate sports. But where else could such real-time, hyper-accurate 3D tracking transform our world next?